Okay, so in this section of this lesson, we're going to be going over the second fundamental theorem of calculus. So yeah, there's not just one part, but there's actually two parts to the fundamental theorem of calculus. And in this second fundamental theorem of calculus, it's still going to involve using a definite integral, but one of the endpoints, the upper endpoint B, is going to be a variable. So instead of it being a fixed number, it's going to be a variable, and we're just going to say x because that's what we're used to. So let's go over the definite integral that we're used to. Usually we have it represented like this. The definite integral is going to be equal to some number, which where that number represents the area of the region trapped between the function and the x-axis. So we have the integral of f of x dx from a to b. A and b are the limits of integration. So they're constants, they're numbers. A could be 1, b could be like 10, but they're fixed numbers. Now, when we're talking about the upper limit b being a variable, then what this means is that f is going to be a function of x. And so that we don't confuse the variable in the integrand with the upper limit of integration x here, we're going to just use t in its place. It's basically just like a dummy variable. It means the same thing that we normally use x for. We just don't necessarily want this x to be the same value as this. So the lower limit, a, will still be a constant, but the upper limit will be a variable. So it's going to be a function. So large f of x will be equal to this integral. This is what the second fundamental theorem of calculus uses. So let's go through a practice problem because it's always the best way to understand these concepts. So let's evaluate the large f of x integral that's equal to the integral of the cosine of t from 0 to x at these values of x. So what we have here, again, is that large f of x is equal to, this integral. But again, you're not going to get some number. You're not going to, because you're getting a function. But we're still going to evaluate this by using the antiderivative, that we applied in the first fundamental theorem of calculus. So we start off and we find that this will be equal to the antiderivative of the cosine of t, which will just be the sine of t. And we're going from 0 to x. This will just be the sine of x minus the sine of 0. Sine of 0 is still a number. Sine of 0 is just 0. So this just simplifies to the sine of x. Because it's just going to be sine of x minus 0. This will fall away. Now, this is going to be our, our function or equation for large f of x. So let's say we want to evaluate large f of x for 0, pi over 6, pi over 4, pi over 3, and pi over 2. So we want to find what large f of 0 is equal to. Large f of pi over 6 is equal to, and so forth. Let me write these out. Okay, so we're simply going to evaluate these equations by plugging those x values into this. So large f of 0 is just the sine of 0. And so you're just going to get 0. Large f of pi over 6 is just the sine of pi over 6, which will just be, as you should know, 1/2. Large f of pi over 4 is the sine of pi over 4, which would be root 2 over 2. Large f of pi over 3 will be the sine of pi over 3, which will be root 3 over 2. And large f of pi over 2 will be the sine of pi over 2, or just 1. Okay, so we end up getting numbers for each of these values. So exactly what the heck is going on? Like, what do these numbers mean? Well, let's start off by just drawing what this represents, geometrically. It's going to be the same principle as what we've learned about deficit integrals, where we're going to be looking at the function, the cosine of t. So let's see if I can draw this well. So the cosine of t. Okay. Yeah, did my best, sort of. I don't think it passes anyways. This is the cosine of t. And this will be, pi, we're going up to pi over 2. So this will be pi over 2. And over here is 0. Now, so what's going on here? So large f of 0 is a sine of 0, we get 0. So this is nothing because we're basically integrating from 0 to 0. So we don't have, any area. So, it's nothing. So that makes sense. Now, f of pi over 6, we're integrating from 0 to pi over 6. So we're finding the area of the region from 0 to pi over 6. In other words, from here to here. So we're finding the area of this rectangle, essentially. And the area here of this rectangle is 1/2. That's what this value represents. Now, large f of pi over 4 is the area from 0 to pi over 4, from 0 to pi over 4. So pi over 4 should be half of this. So essentially then this entire area. And that we got to be √2/2. And so forth. This is essentially what's going on. Pi over 3 would be the area from 0 to pi over 3 of this. That'll be √3/2. And the total area from 0 to 1 underneath this graph is just going to be 1. So you want to think of this function as like an accumulation function. It's basically going to be changing its value depending on what you want the endpoints to be. So it's still representing an endpoint of integration, but those endpoints, will vary depending on what you want to, where you want to integrate up to. So that's kind of the cool part of it. Now let's look at this in more detail and how we can apply it algebraically. So it's actually quite simple. The second fundamental theorem of calculus says that let's make it so that we're gonna rewrite the function as small f of t dt. So the integrand is small f of t dt, and we're gonna integrate from 0 to x. Now, when we take the derivative of an integral, you're basically undoing the integration process. So this integral operation essentially goes away, and then you just are left with f of x, or small f of x, to be specific. And it's really that simple. I'm not going to go through a proof in this video, but if you want to understand what's going on here, and you want to follow a proof, make sure you look at the other video, because it's going to be quite intense. It's not that simple, but it's cool to know. Anyways, so how do we apply this? So let's say we want to evaluate this. And it's really simple. If we want to evaluate this integral, if you want to find the derivative of this integral, since we're simply integrating from 0 to x, all this means is that this will simply be equal to, we just replace the dummy variable t with x. So this will be equal to the square root of x squared plus 1. And that's your answer. That's it. Remember, you're going to be left with a function as your answer. And when you differentiate an integral process, you're undoing the integration process. So you're just left with the integrand, whatever the expression is on the inside. That's it. Now let's look at another graphical example of, of what's going on with this sort of function, so we can gain some more conceptual understanding. So here we have that f of a function shown here, and we have that g of x is equal to the integral of f of t from 0 to x. I want to find g of 0, g of 1, g of 2, g of 3, g of 4, and g of 5. So similar to like the problem that we just did on the previous page, g of 0 will be equal to the integral from 0 to 0 of f of t dt. Now there's no area underneath, the same point, so this is just going to be 0. Now remember, we were not given the equation for f of t. This is why we're going to do this geometrically. Now g of 1 will be the integral from 0 to 1 of f of t dt. So what we do is we look underneath this function from 0 to 1, and we calculate that area. So we're looking basically the area from here to here. So we're looking at the area underneath this line, which is just the area of this triangle. The area of this triangle is just, going to be 1/2 base times height. The base is, 1. The height is 2. So 1/2, 2 times 1. So the area will just be 1/2, 2 times 1, or just equal to 1. So that g of 1 will be equal to 1. And I mean, I don't want to, that one actually kind of looks confusing. Now g of 2 will be the area from 0 to 2. So we set up our integral like this. And we can calculate this by adding the area of this triangle to the area of this rectangle here. The area of this rectangle here is 2. So this will just be 1 plus 2. And then this will be equal to 3. And we just keep on going. G of 3 will be the integral from 0 to 3 of f of t dt. I'm going to guess this is supposed to be the trig function, because we're not given the exact value of this. So we'll take a rough approximation. We'll just say that this is, essentially the area of this triangle. So this is going to also have an area of 1. So this will be 3 plus 1 plus 2 plus 1. So this will be just 4. We'll say approximately 4. It's a little more than 4. But the reason I'm just going to make it 4 is because this is going to be erased by the area up in the next integral. So g of 4. So we integrate from 0 to 4 of f of t dt. Like, again, this was curved. We did an approximation. We just approximated that to be 1, but this is positive. This, what we're going to assume, is symmetric. This is negative. So this area here essentially cancels out with this one. So whatever this is going to be its opposite. So these cancel, so it's just going to be 1 plus 2. Because if we were to say that was 1, then this would just be minus 1. So those would cancel. So we could say it's about 3 still. Let me shade it on the way. And the final one, g of 5 will be the integral from 0 to 5 f of t dt. we're going to add this final part. And again, we'll just say that this is we'll just say this is about -1. Say there is about -1. This will be equal to 3 minus 1. So about 3 minus 1, so equal to 2. We'll just say. So that's what's going on with this function here, which is, you know, essentially how we use the second fundamental theorem of calculus in action. Now let's actually make a graph of what's going on with g of x to see how it's behaving, because this is going to be a good way for us to understand how we're going to apply this further down the road. So we're going to make a graph of, you know, we're still going to have the same values of x. So 1, 2, 3, 4, 5. And we're going to have g of x be graphed here. So g of 0 will be 0. So we're going to have a point at 0, 0. And let's go it's 1, 2, 3, 4. Now, g of 1 is 1, so we're going to have a point at 1, 1. G of 2 is 3, so we're going to have a point at 2, 3. G of 3 is 4, so we're going to have a point at 3, 4. And G of 5 is 2, so we're going to have a point at, or no, G of 4 is 3, so we're going to have a point at 4, 3 again. Or sort of again. And then G of 5 is 2, so we're going to have a point of 5, 2. And since we know this is continuous, we can connect these. You know, it looks like this is pretty much going to be linear across the whole way. And this is going to be our graph of g of x. So you can see that it's increasing first. If it's increasing, then it reaches a max here, then it starts to decrease afterwards. So again, the second fundamental theorem of calculus essentially describes a function that can be thought of as an accumulation function. It's accumulating the areas up to the x endpoint. Okay, so one more problem where we need to know how to apply this. So let's say we want to find the derivative of an integral where the endpoint simply isn't x, it's x cubed. So what do we do here? There's actually a couple ways to go about this. You can actually use the chain rule, where we're going to use substitution or substitute a dummy variable for x cubed. I prefer just to go about it by taking the derivative. I think that's more I think it's more intuitive and you know, easier to follow and easier to understand, which is what I like. So in other words, we go about this like normal. Like we find the antiderivative of the cosine of x. So large f of x will be equal to the antiderivative of the cosine of x will be the sine of, or in this case, t, sine of t. And we're integrating from x cubed, or we're integrating from pi over 2 to x cubed. So this will be the sine of x cubed minus the sine of pi over 2. Which will be equal to sine of x cubed, sine of pi over 2 minus 1. Now, we're trying to find the derivative of large f of x. So we're actually trying to find large f prime of x. So this will just be the derivative of this. So we just take the derivative of this with respect to x. So we're applying the differentiation operation. So using chain rule, we're going to multiply this by the inside derivative first. So the derivative of x cubed is 3x squared. Multiplied by the derivative of the outside function. So the derivative of the sine function is the cosine function. So times cosine of x cubed. And the derivative of -1 is a constant, so it's just 0. So -0. So it doesn't matter. So your answer is just this. All right. And that's all there is to it. So good luck.